This is a great problem. So you have this snowboarder. He starts at the top of the ramp and he slides down the ramp, and there's some friction. And then he has some velocity down here where the height is zero. So he's all kinetic energy. And then he goes up this ramp and he goes on this trajectory, and we're given the horizontal velocity that he has here is given. And we want to know what is the height. Um, what's his peak height? So I looked at this. So basically, here it is in a nutshell. He starts up at this height with zero velocity. He has um, a certain energy, and it's all potential energy because he's not moving. Okay, so what's his potential energy? Um, his potential energy, I just labeled it E1, made up that variable, and it's just mgh1. Okay, where h1 is his height, and um, as he slides down here, he starts to accelerate. So his energy, some energy is just lost, just burned off because of this friction. And we know this friction because we're given a friction coefficient. Um, but he's moving, and so he's losing potential energy because his height is decreasing, and he's burning off energy because of this friction. But he is accelerating, so he's got velocity. So he's picking up kinetic energy. He's picking up kinetic energy. Down here, all he has is kinetic energy. He doesn't have any potential energy because he has zero height, but he's got a velocity, which we don't know what it is, um, and we don't have to have the number. Um, we might just want to write the expression for it. But anyway, he goes up this ramp, and we are given, this velocity, horizontal velocity component, and we want to know what the height is. So, first of all, we have to figure out what is the starting height, and we can do that with just some geometry. Um, we've given this angle, so we can say, well, the sine of 30 equals opposite, which is h1, over the hypotenuse, which is this distance, 50, that we're also given. So that gives us h1. So we can write an expression for his initial energy, which is important. So that's just mgh1. And we have to resolve these forces because we have to know, there's a frictional force. The frictional force always goes the opposite direction of the motion. But we have to figure out this frictional force. So that turns out to be not too bad because we can just use the triangle technique to resolve the forces. And we know this force is always acting mg straight down. We need the normal force, which is the force on the plane, on the contact area, Fn. I labeled that, and we can just get that with these little trig relationships. Now I drew a similar triangle here, and see this 30 that we're given here? That 30 there is that angle there. How do you know that maybe? Well, just imagine moving these things, moving this line. If you reduced this angle to 0, this angle here would be reduced to 0. And you can sort of play those little games to check. But anyway, that's a right triangle. So I said sine of 30 opposite over the hypotenuse. Sine of 30. This opposite is the FD force. So sine of 30, FD over mg. I wrote it down. FD. I don't even know if I'm going to need it or not. I just wrote it down. And then the cosine of 30. I know I need that because that's just normal. Cosine of 30 is adjacent over hypotenuse, right? So that's that one. I know I need that, Fn. So just rearrange a little algebra. Fn equals mg cosine 30. And yeah, so we write, we figure out his initial energy. We figure out the energy that got burned off because of this friction. And that energy is the work that was done generating heat. And that's just F times D, the force times the distance, just like pulling a rope a certain force, a certain distance. How much work did you do if you pulled a rope, a certain amount of distance? So, anyway, I'm going to leave this as a to be continued, but anyway, you can just ponder this stuff right here, and then this is the rest of it. So I pretty much figured out how much energy he had right here after burning off, creating that heat with friction, how much energy he has here. And then that's easy once you know that, because right here it's all kinetic and no potential. And here he's got both. But guess what? You know what the kinetic energy is. And you know that the sum of kinetic plus potential equals this energy down here he had. Because nothing was lost when he went up this ramp. Because we're assuming there's no air friction. So anyway, that's what's done here. And these are the units checks. Very important. You get credit for this. And I did these checks and I found a mistake that I made in the algebra. So that was handy. Glad they made me do that. Anyway, I did this plug and chug, and yeah, so there's the answer I got for that height. And yeah, you want to work this yourself. You want to watch this and then just try to work this yourself. And if you get stuck, go back to this, watch it, and then put it away, and then again go back and work it yourself. Yeah, that's it. Thanks for watching. Don't forget to give me a like, please.